Thank you very much for coming. As Flora is not here today, I'm going to introduce Kacper for you. So Kacper Sokol, he is a research fellow at RMIT University. Before that, he was a master and PhD student at the University of Bristol, UK, where he worked with Peter Flack. And his research focus on explainable AI. So he's going to talk today about a talk with the title, Never Let the Truth Get into the Way of a Good Story, the Importance of Multilevel Human Understanding in Explainable Artificial Intelligence. Kacper, thank you very much for accepting our invitation to be here today, and the floor is yours.
Amazing. Thank you. And thank you for coming. Right. So this talk more or less follows my journey with explainable AI. And when I got into the field quite a few years ago, it was a mess. It was a very new thing. Everybody did something, and I couldn't quite figure out what to do. So I decided to organize things, start collecting all of the properties that people use to describe explainability, to guide the design of new methods. And in the end, this constituted a taxonomy of explainable AI that I call explainability fact sheets. So this cover both social and technical aspects of explainability, and there are split in 5 dimensions. So this describes the algorithmic requirements, user-centered properties, deployment settings, robustness, security, as well as how the methods were evaluated. So this gives you some framework to reason about explainability because we compare the methods. And this was intended for both researchers, so people who create these methods, but also practitioners, so people who deploy them, who use them, engineers or data scientists, but then also personnel that inspects data-driven methods, machine learning models, AI, either policymakers or auditors. They can be operationalized as fact sheets, so that's the main use case, to assess and compare these methods, to know what they do and what they don't do. But they can also be used as worksheets. So if you're designing a method, you probably want to follow some rules, try to decide what the method should do, what the method can do, but also checklists. So this more or less correspond to the three target audiences that I have in mind. Then they apply to both the algorithms, implementations, and the theory behind explainers. And that's because this can differ quite substantially. So for example, you can have an explainer that promises you a lot of things, but when it comes to implementing it, it's not computationally feasible. So you do use a few proxies and then you lose a few of these good properties. So you should probably describe all 3 aspects of your explainer, and then also highlight where it diverges, where the differences are, because even if a paper or the algorithm promises something, the implementation basically may not deliver, or you may have multiple implementations all focused on different things. As I go through some of these properties first, I just want to have a running example in the background so that I have something to refer to, and this will be counterfactual examples. So this can either be textual here, so had you been 10 years younger, your loan application would have been accepted, or image counterfactual. So here you can see that a part of the image is removed, this black bit here, and then the prediction changes. Right, so let's get on with this long list of properties. I won't cover all of them because I think there's at least 30. I'll just highlight a few and then move on to more interesting stuff. So for the functional requirements, these are properties such as to what models the explainer applies. So whether it can apply to any model agnostic, whether you have to use a particular class of models, for example, differentiable models, or whether it's specific to a very unique model. Then what's the relation with the predictive system? Whether it bases the explanations on the information directly from the modeling aspect, or whether it's yet another technical block that you put on top of your machine learning model and then generate these explanations. You can also describe the explanation target. So what are we trying to explain? Is it data? Is it models? Is it predictions? And counterfactuals are specifically designed for predictions, and you could have seen that. It was the prediction that's being explained. The prediction will be different if you change some aspect of the model, of the instance. And then what's the scopes? So is the explanation local? And again, this was the case with the counterfactual. It was just for this particular data point. Is it cohort, so for multiple instances, or is it global for the entire model, the entire data set? Let's move on to usability requirements. So here you can study properties such as soundness. So how truthful is the explanation with respect to the black box? Ideally, you would want it to be truthful, to be useful as an explanation. And counterfactuals should be that because they rely on the predictive model itself. They try to find the decision boundary and move the point to the other side of the decision boundary. Then how well does it generalize? And unfortunately, counterfactuals, unless they're generated with causal models, do not really generalize beyond the particular instance that they were generated for. And then whether they are provided in a context. So because they don't generalize, you may want to show how they can be applied safely to other instances. So here, for example, you may say, oh, this counterfactual applies to everybody who's older than 25. And then obviously you want explanations to be short for them to be comprehensible. So, and again, counterfactuals satisfy these properties because in the foil, so the condition of the explanation, you usually use just one or two features. Then are they actionable? So can the user see the explanation and then change his or her situation? And this depends on the foil. The counterfactual that I showed you, the textual one, was not actionable because it was based on age. You can't change your age. But if you use a different foil, then it is potentially actionable. Then is it interactive? So can user tweak the explanation? Can the user interact with the explainer such that he or she can personalize the experience? So get a counterfactual that is useful for the problem that the person is trying to solve. So for example, if you're applying for a loan, you may want the counterfactual that is based on your income or your credit history. Then for the operational requirements, these are, for example, what family does what family of explanations does your method belong to? So counterfactuals provide you with contrastive statements that highlight the differences between the instance and the foil and the change in class, but you can also have causal mechanisms or associations between some aspects of your model, of your data point, and the consequence. So for example, feature importance or feature influence in this case. Then what's the explanatory medium? How do you communicate the explanation to your user? And I showed you two examples. One was a visual counterfactual, the other one was a textual one. But you may also want to use formal argumentation or just summarization if your target audience are engineers. And then also, can you actually interact with this? So you can see that there's quite a lot of overlap, but that's because some of these properties deal with technical aspects of the explainability algorithms, whereas others deal with social aspects. Then what's the domain that you use to explain? So you may use the original feature space if that's intelligible to your users, but you may also need to transform that into something else. Then this may be because the data or the model itself is not transparent. So extracting the parameters of your model may not be of much help. And then also, what's your target audience? Are we targeting here domain experts or lay audience? Then the last two, which are safety requirements. So you may be interested whether when you introduce explainability, does it leak any information? In case of counterfactuals, they do leak possibly the decision boundary, because if you're trying to push the point across the decision boundary to get a different prediction, then if you optimize it with respect to that, you will more or less know where the decision boundary is. So then this possibly allows you to misuse the system. For example, either reverse engineer this part of the decision boundary or try to tweak your instance or the situation such that you get the outcome that you want. And then also, is the explanation invariant? So if it's based on an algorithm that is stochastic, will you get a similar explanation if you repeat the explanatory process? And then finally, what's the explanation quality? So is the instance in case of counterfactuals that you get from the distribution of the data, or maybe it's very close to the decision boundary, which is fairly dangerous because if you retrain your model, then it may not be a counterfactual explanation anymore. It may belong to the same class. For validation, you can either do user studies or synthetic experiments. And there are a lot of problems here, and this is still very much an active area of research. because you need to take into consideration the correctness of your predictive model, the correctness of your explainability algorithms, whether the explanations are useful for the scenario that you're deploying them in, etc. Right, so let me just talk you through 3 examples. So one is from a researcher's perspective. So you may have a model that outputs numbers. Now, if you have an explainability method that works with numerical outputs, then a reasonable question to ask is, can you apply it to a regression model? And can you also use it with probabilistic output of a classifier? Because it may have been designed with a particular use case in mind, and you're breaking a lot of assumptions if you're not following guidelines. So fact sheets are supposed to help you go through this sort of reasoning and try to figure out whether what you're deploying is actually reasonable. And then also, if it works with numerical features, well, you're only with numerical features, well, your dataset may have categorical attributes. So then the thing to do is to just hot encode them and use the algorithm anyway. Does that break any assumptions? Are the explanations still useful and truthful? Then as an engineer, let's say that you want to deploy something that explains song recommendations. And then because it is directed at the users of, say, a music streaming service, you want the method to be based on the user listening habits. So that's what you want as the main message when explaining. And then you may want the explainer to provide something that's actionable. So for example, if the users don't like what they get as the explanations, they know, well, as the recommendations, they know how to tweak the system, how to interact with the system to actually help it guide towards more useful recommendations. And then if they want to deploy it in real time, thus the computational complexity of the algorithm actually allows for that. And as an auditor, these are the 2 use cases that I explained. So does it leak any sensitive information, especially when your predictive model is proprietary? And then also, if you provide context, the context of the explanation can also leak information. So it's important to check all of the aspects. And then does it allow for abuse of the predictive model? So for example, if you get a lot of counterfactual explanations and you learn that the threshold is a round number, you may want to then round your salary up a bit just to push you across the boundary. And then how it was validated and whether it was validated in the very specific context in which it is deployed. Because for example, if you validate your explainer in a music recommendations setting, you don't really want to deploy it in a medical setting, so high stakes domain, because it may not be tested or intended for that purpose. We did provide an example of a fact sheet, and it's available alongside the paper that it's done for Lyme. And obviously, this does not solve all of the problems. It just allows you to highlight the problems that you find with explainers. So first of all, it's neither exhaustive nor prescriptive. Some of the properties are incompatible. So if you want to optimize for one, you may need to give up a bit of another. And also, you may have competing properties. Many of these cannot be answered uniquely, and that's because it depends on the deployment scenario and how your system operates and in what context. And most importantly, even though we can list all these properties, they do not really define explainability. So that is what I kind of tackled next. What is explainability and how can we get there? Well, there are a lot of definitions. People try to define explainability. One is simulatability, which I personally do not like. But simulatability basically states that if you are able to mimic the predictive process, the decisive process in your head or using pen and paper, whatever it means that something is explainable if you can replicate it. There's actually an argument against it that predates simulatability, and that's the Chinese room theorem. It more or less describes a situation where you lock up a person in a room and the person gets all of the resources necessary to translate Chinese into English. And then you slip a note under one door. The person, however long it takes, translated using all of the rules and guidelines in the books, in the resources provided, and passes out the note on the other side in English. So the task has been completed. The note has been translated from Chinese into English, but that does not necessarily mean that the person who does the translation understands either English, Chinese, or whatever was in that note. Uh, Another approach to defining explainability is via mental models. So there are two important ones. First one is functional. So you know how to operate a concept. For example, if you want more light in the room, you know that you need to flip the switch and then the light turns on. This does not necessarily mean that you know how the electrical circuits work or the physics underlying this process works. So it doesn't really generalize to a lot of other concepts. Whereas a structural mental model gives you more in-depth understanding of the processes that go behind that. So then you can use this knowledge to try to figure out how light switch works, but then you can also generalize it to other contexts that deal with electrical circuits and possibly physics. So that led me to define explainability as reasoning, whether done by humans or algorithms, that is applied to transparent insights. So you have to extract these insights from your machine learning model or data-driven process, and you need to reason about these insights in view of your background knowledge. So depending on what background you have, you may interpret these insights differently. And in the end, explainability should lead to understanding. That's what you're striving for. That's what you want. You want people to walk away with understanding, however you achieve that, which again is fairly, yeah, go for it. Yeah, go for it. Yeah, yeah, that, yeah, yeah, it's as generic as you want it to be. Whatever context, I probably should make it more clear. Yeah, probably, but yeah, it's under the background knowledge part of the equation. So yeah, all of the operational context is in there as well. And then it's important to note that none of these concepts are binary. So we're not talking about, is it opaque, is it transparent? It is usually placed on a spectrum. And again, that depends on the operational context. The same piece of information, the same insight into a data-driven process may be transparent, more transparent to one person than to the other. And then you need to account for that and adapt your explanations. Now, the important part of the definition are humans, because they more or less establish the context and the background knowledge that is brought into the definition of the explainability. And this hasn't always been the case. So it used to be a very technical field, explainability. We only cared about numerical things, and we optimized for some metrics, usually arbitrarily chosen. And then Tim came along around 2017, and he said, wait a minute, there's a human there, and you probably want to satisfy that person's needs to explain. So the explainability usually arises when there's there's lack of understanding, or there's a mismatch between your expectations and how the model behaves. And two of the important properties of human-centered explanations are that they tend to be contrasted, at least between humans, and they are usually placed within a dialogue. So it's not just me coming here and giving you an explanation and walking away, because again, you may come with different assumptions, and we need to iron all of this out. So yeah, that's true. Oh, sure. Thank you. Uh, so the question was why there's no, oh, what was it? No, I lost it. The question was why there was no context in the equation, such as the situation in which the explanation takes place, or the explainer is deployed. Right. Uh, oh, oh, that there's, and then again, with respect to the same, there's no interaction there, which probably should be an arrow around it. I'll think of it. Right. So humans are important. That's the bottom line. Exactly. That's an explanation. I'm explaining my research. Perfect. So now let me show you an example of an explanation. This may be informative to some of you. It's a linear equation. But even if you know what it means, there are a few assumptions there. So if you want to treat this formulation as an explanation, first of all, you need to assume that the features were normalized to the same range in order to compare the coefficients. And second of all, you assume feature independence, so no interactions between features. And then only you can interpret the numbers in the equation as importance factors. Then if a data point comes in, you need to do some reasoning. There was a reasoning in the equation as well. So this is where the reasoning comes in. You need to apply this equation to the data point, and then you get individual contribution to the prediction of each feature for this particular instance. So first of all, it requires background knowledge in computer science. And then you also need to clarify the assumptions. You can take part of this reasoning away if your target audience does not possibly have computer science background. So then you can plot the same thing with a bar chart. And this simplifies a lot of things. It hides a lot of complexity, but it may be easier to understand. So here again, you only have contributions of features for this individual instance and the final prediction, but you don't get the equation itself. And then you can simplify it even further. So you can use a force plot to represent more or less the same information, which possibly is even more informative for a lay audience. So there's a lot of things happening here, but in the end, you end up with a prediction 0.6, and then some of the features push it more to the right, to the higher prediction, and others to the lower prediction. So you don't need that much technical depth in order to interpret this explanation. Right. Now I'll briefly talk about evaluating explainability. This is an ongoing line of research, and then I will move on to something more interesting. So this is more or less the framework within which I think we're operating when we're dealing with explainability and machine learning models. So you have some natural phenomenon that generates data that you capture, use this data to train your model. This model spits out predictions. Then possibly these predictions go into the explainer. The explainer generates explanation for your explainee. The explainee ideally can interact with all these components, including the natural phenomenon. So for example, if I want to test gravity, I can just drop something and hopefully it falls down. So then these experiences allow me to build my mental model. And this provides me with understanding. And ideally, explanations either fill in gaps in my understanding, provide me with new insights, or correct false beliefs that I have. But usually what happens is we just ask, does the explanation work? You probably use mechanical Turk, get a bunch of random people, show them something, and you ask, is it helpful? Well, that doesn't really tell you much other than allowing you to publish your paper and claiming, oh yeah, it works. It's better than the other method. So we probably should dig a bit deeper. And I think there are two important things here that are not taken into consideration. So once explainability moved into the human-centered area, we focused a lot on humans and kind of forgot about these technical things that these algorithms that generate the explanations. So here, I think it's useful to separate how the explanation is communicated, what sort of method we use, how do we visualize, whether we visualize, whether we provide textual explanations, and whether the explainer itself is correct and whatever it produces, whether these insights are correct. Because, for example, if you have a very nice system that is convincing to people, but the insights that you generate, your method is wrong, then you're just misleading people and are potentially harmful. If all is good and you have a convincing communication paradigm and correct explanations, then these are factual explanations. This is where you want to be. And then you can waste your effort if it's a correct insight, but you're not communicating very effectively. And then oh, that's true. Yeah, again, I need an arrow from right to left. So yeah, if people misunderstand them, Well, but that's on them, right? You okay? Right. So the question was, what about the misleading explanations? So when people misunderstand them, uh, right? And then there is another aspect that not many people consider, and this is whether the predictive model that you have is consistent with the natural world. Because if you explain a prediction that is incorrect, then you can't really use it as an explanation unless it's an explanation for why the model failed. But this involves the human there judging whether uh, the explanation is correct. So you also need to take care of your model. You can't just focus on the explainer itself. There's this whole ecosystem of natural world and your model, data, probably pre-processing, etc., that may affect the explanations. And we all need to we need to take all of this into consideration. So that's why asking a question like, does the explanation work, is insufficient. Right. So now that we've covered all of that, we can do the interesting bit, which is a case study of surrogate explainers. So I will be using Lime as an example, and here the shading in the background, so pink and blue, that's your complex decision boundary, your black box. And then you're trying to approximate it locally around the bold plus symbol with a linear model. So surrogates approximate a complex decision boundary with a simpler model. Why people like them? Well, first of all, they are model agnostic. So whatever model you have, you can use them. They're post hoc, so you don't really have to think about explainability from the very beginning. Once you have your model, you can then only you can then make it explainable with post hoc methods. And they're also data universal, so you can use a thing called interpretable data representations, which I'll cover in a moment. And this allows you to have the same looking explanation for images, text, and tabular data. But of course, we know that there are no universal things. So this is where the no freelance theorem comes in. It more or less states that a single solution cannot outperform all the others across the board. And this is the case with surrogates as well. So Cynthia has shown that they tend to have poor fidelity, which means if we go back to this example, they don't really align that well with the black box decision boundary, which means that the explanations can be misleading. So she argued that we should actually develop a process for designing and building explainability and base it more or less on the processes that we have for data mining, such as KDD, CRISP-DM, big data. And then focus on feature engineering and actually design models that are interpretable from the outset rather than just go with whatever gives us the best performance and then use post hoc explainability. But it requires effort. So, and then with the post hoc methods, you just deploy the same thing, whatever your use case is, and you get something out of it. Whether it's an explanation, that's a different discussion. So can we actually design a generic XAI process? Not really, we're not there yet, but there are some attempts. So one of them is the XAI taxonomy that I introduced at the very beginning. So this allows you to reason about your method and kind of try to judge whether it's suitable for the use case that you have. And then there are other frameworks, more technical, that try to describe this process mathematically, but again, they are fairly restrictive. And while we can't design it in general, we can actually do one for surrogates, and that's what we did here. So BLIME stands for Build BLIME Yourself. BLIME was the method I introduced a few slides ago. And this is a framework for building surrogate explainers. It allows you to think about different aspects of your problem and try to design this these explainers such that they fit your particular use case. There are three components there. So one is data sampling, the other one is interpretable representation, and the third one is data generation. And I'll cover them in a moment. So the good news is that we actually can make surrogates useful, faithful, and working as intended. However, it requires effort. So it kind of breaks the charm of Posthog explainability. But then in order to operationalize them, we actually need to understand where they come from, what sort of assumptions they're working on, and also how to interpret them, because it's usually not that simple. Even though you get a nice bar plot and you have some intuition what it means, that is not necessarily your intuition does not necessarily correspond to how this information should be interpreted. Right, so let's have a look at surrogate explainers for images. So how do we map the concept of surrogates with actual explanations? So here, bottom left, you see the explanation, and it tells you how important, how much influence each part of the image has on predicting golden retriever for this particular image. How do you achieve that with surrogates? Well, so your interpretable representation, so something that you can communicate with your users, is generated by partitioning the image into regions. And that's what you can see in the bottom right. So you split the image into non-overlapping segments. Then data augmentation is occluding different patterns in that image. So you're basically trying to figure out whether how influential each segment is for predicting a particular class, in this case, golden retriever. And then for the explanation generation, you use a linear model. You fit the linear model into this random occlusions of the image, and then the predictions of these randomly occluded images that you extract from your black box. The missing link is how do you actually train your linear model, your local linear model on the images? And the answer is you represent them as binary vectors. So what happens here is once you partition your image, you represent each fragment in a binary vector. It's 1 if you preserve the original pixel values, and it's 0 if you remove that part of the image. So for example, occlude it with solid black color. And you use this together with predictions, black box predictions of these images, one of which you can see in the bottom right, to train your local linear model. And from that model, you extract your coefficients. And these are the things that you plot as your explanation. Yeah. So what happens here is so the question was how linear model generates these explanations. How does it constitute the it is the explanation, right? So what happens here is that if you train your linear model on a bunch of these vectors as your training data, binary vectors, and as target you use black box predictions of these partially occluded images, what the linear model is supposed to do is to capture the importance. So when the importance of each super pixel, each patch being present, and this is represented as 1. And yeah. Yeah. Right. So then you'd ideally hope that, and I'll discuss it in a moment, you'd ideally hope that what your idea of this being a golden retriever is would kind of converge, well, would be more or less the same as what the weights pick up. So ideally you would want to see green regions around the face of the dog, because that's what you pick up as a human when you explain this. But this is not necessarily the case, and I'll show you why this all breaks down in a moment. So this is the prediction of the image. So I'll show you an example why it doesn't work and why you don't like it as an explanation. So this image is mostly predicted as a tennis ball, and then you also have some prediction for golden retriever and Labrador retriever. The explanation for the tennis ball is more or less reasonable, right? Because there is the region with the ball and it appears in the explanation. It's not at the top, which is what you would expect. And there are also some artifacts. So background is shown as being providing negative evidence towards this prediction. And then part of the dog's face is providing positive positive information for the prediction. Now, if you do the same for golden retriever, that's even less helpful, because what it tells you is if the ball is not there, then it is a golden retriever. That's useless. So we run through a few of these examples and we decided to investigate it a bit further. And this is what's happening here. So there are two parameters that come, more or less, two parameters that come into this sort of explanations. One is the color that you use for occlusion. So on the right here, you can see these different randomly generated images that were used to train the model. And then you can change that occlusion color. And if you pay attention, you can see that the explanation changes as you change the occlusion color. So that's not good, right? And then the other aspect is the number of segments that you generate. And again, you can see that as you increase the number of segments, different regions become important. So there is some variability there. And what we wanted to do is investigate it a bit further. So what happens here is we split the image into 5 segments, and we start occluding random patterns with 1 segment, 2 segments, 3 segments, 4 segments, all of the segments, using different occlusion colors. So here you can see that, and on the y-axis, we measure whether partly occluded image can still be predicted with the original class, and what's the squared error between the original probability of that class and the probability of the same class when the image is partially occluded. So here you can see that all of the colors more or less behave the same. But as we increase the number of segments, there's one color that stands out, or at least one occlusion pattern that stands out. And that's the mean occlusion color. And if you think about it, that actually makes sense, because if you go with the mean occlusion color, so this means that you replace each superpixel with the average color in that region. It's not really removing information. It's just blurring the image, especially as you increase the number of segments. So if you sit far away, you may not even notice that the image on the right is being occluded. And when I increase the number of segments to the maximum here, you'll see that that's even more pronounced. There's another important point to make here. Even though you can study the overall effect of these properties on the explanation, you can still not cover every single unique case. So if we try to explain the tennis ball, what do you think is the worst possible choice for the occlusion color? Remember that the occlusion color is supposed to remove the information from the image. We can try red. Oh, I don't have red. You got me. I only have, okay, there's black, white, random, so you can generate random patches, or green. Yeah, but what's the worst one? Not what's the best one. So you can see that if I use green, the ball is not part of the explanation anymore, because if you replace the ball with green, you still have a ball, it's just smoother. So even though you can study these global effects, you still should pay a lot of attention to your particular use case. And then we did the same for tabular data, but that's a bit more complicated, so I'll skip that unless you're interested. So what comes out of it, right? First of all, each explainability scenario is very much unique, and you ideally need a bespoke solution, especially if you want to deploy it in the real life. You can't just get off the shelf. You can't just get off the shelf explain and hope that whatever insights you get constitute real explanations. Then explainers are a socio-technical construct, so you should care about both the technical correctness of your system and the quality of the explanations, possibly any randomness that comes into it, anything that may adversely affect it, but also how you communicate these things to your users and whether there isn't any miscommunication or any misunderstanding happening because of the interaction and how you present the insights. Then explainability algorithms are not monolithic entities, and you've seen that with surrogate explainers. There are 3 components, and depending on how you tweak these components, you may get completely different explanations. So for example, instead of a linear model in surrogates, you could use a decision tree, and then a decision tree would tell you something else. It would tell you, oh, if this segment is preserved and the other segment is preserved, then the prediction is that. So you get different kind of explanation if you use a different surrogate model. And then again, they need to be configured for the problem that you're facing. So for example, if you're trying to explain a tennis ball with a surrogate, you should not use green as your occlusion color. Then these are in general technical diagnostic tools, and only if you know all the assumptions that they operate under and how to interpret the results, they become explainers. Otherwise, you may misinterpret whatever insight they produce. And then ideally, you'd want more insights, different insights, more diverse insights. So a single explanation may not necessarily give you the full picture. So you want to probe this mechanism from different sides using different methods with different assumptions, and ideally try to come up with a truthful story. And then in the end, you probably should ask yourself, do you really need this very complex model to solve your problem? Because there may be simpler solutions that are more transparent, more interpretable, and achieve the same goal. In the interest of time, there is a bunch of resources that you may want to have a look at. There is a software package that allows you to generate this sort of explainers and play with them. We had a hands-on tutorial at DCML PKDD 2 years ago, also covering similar topics, how to design good explainers. I did a bunch of summer school sessions, seminars, etc. Most of these are recorded. There are a lot of computational notebooks available and examples that you may want to have a look at. And together with the Alan Turing Institute, we hope to publish at some point in the future a bunch of resources on that topic, but that very much depends on manpower that we can get. So that's coming up at some point in the future. Right, thank you so much. If you'd like to, I can go back to the tabular surrogate example. Otherwise, I'm happy to take questions. So, well, the classified tries to predict the class. Does it really matter? Yeah. So what I'm explaining is how the model predicts the image. I'm not explaining any. Well, it's a black box. It was a neural network, so it is based on correlations. It doesn't really take into consideration the real world, which means whatever explanation I'm showing you, you should not compare that with your. Yes, so that's the problem with surrogate explainers, and that was one of the messages, that if you ignore all of the background and all of your modeling setting, and you just go for Posthog explainers, which you can use with any model just because they work. If you first optimize for predictive accuracy, and then you think, oh well, I also need some explainability, and you get one of these off the shelf, plug it in, then it spits something out, then that's not explainability, and you're right. I here very much agree with Cynthia that you should take into consideration the provenance of your data, any problems with the data collection mechanisms, how you engineer your features. You should put a lot of effort into designing transparent models, as opposed to having explainability just when you realize you need one. It's not explainability, you're right. It's something, but it's not explainability. And the question was that I'm not explaining the model. Yeah.
Okay, thank you so much for a very illuminating talk. So right at the beginning of your presentation, you mentioned several different models of explanation. But the one that you didn't mention is the one that's probably most popular across all of scientific explanation of models of the same, which is the causal model of explanation. And that is to provide an explanation of something is to explain the causal mechanisms that cause it to be the case as opposed to not be the case. And usually discussion of counterfactuals in relation to models of explanation are because a counterfactual analysis of causation is, as things stand, the best analysis of causation that we have. So two questions. One is, why have you ignored causal models of explanation? And if something is not, if some statement, some attempted explanation is not supervening on causation, is it really an explanation? And secondly, what is given that you're not speaking about causation here, what is the connection between the counterfactual, the exposition of counterfactuals you gave at the beginning of the talk on the one hand, and the rest of your talk on explanation on the other, given that causal models of explanation played no role?
Right, great question. I actually agree. It should be a causal model, but they are very difficult to develop. They are problem specific. So if you're doing research on explainability, then if you want to do well, you wouldn't really go for proper explainability, I suppose causal explainability, because it takes a lot of time to develop and then it's just a toy example. In the real life, yeah, you should definitely go for a causal model, but they are super difficult to develop. And the second part was, what's the relation between the counterfactual that I showed and the causal counterfactuals? Well, so right. So counterfactuals are great, but like you've noticed, there are two types of counterfactuals. Right. So so there are two types of counterfactuals that are easy to confuse. Most of the literature uses counterfactuals just as conditional statements, contrastive statements. So you only care about your model. You don't care about causal mechanisms. And then, such an explanation looks pretty much the same as a causal counterfactual explanation, but one of them is based on a causal model and gives you a really good insight into a particular decision, whereas the other one only tells you what to do to get across the decision boundary in your predictive model. Yes. Yes. Contrastive conditionals. That's what they probably should be.
I saw you try to explain the classification of the objects in the image, for example, tennis or dog. And then my question is, how deeper of the level of the neural network you can explain? So I saw you explain by colors, maybe by shape as well. But do you also could explain more deeper level or based on pixel level, maybe lights or?
Right, so these are post-hoc methods, which means you don't care what the model is. You only care about the inputs and the outputs. And then you only operate with these. So and then it all boils down to how you design your interpretable representation. So here, the interpretable representation was based on superpixels, so objects, and then they color because you change the color. Ideally, if you have a way to transform the image in a meaningful way and then feed it back through your model, then you could gauge the importance or the influence of different factors. But this is just a very simplistic setting when you just operate on pixels. Then if you don't want to go with regions, you can go back to raw pixel values, but that's not very helpful. because telling you if you change these 2 pixels, if these 2 pixels are not there, the prediction is different. That doesn't tell you much. Whereas operating more on patches of the image is more meaningful to humans. Because, for example, if this were designed properly and done carefully, you'd design the segmentation by hand and then separate the ears and the background and the ball. So it would be more handcrafted, but then also more meaningful. If you want to automate it and use out-of-the-box solution, you will not get that. Okay, do you want to?
So there's an online question from Lukman. I'm wondering about the audience here. Who are these explainers for? The image segmentations you show seem too technical. So while something broader like this AI is trained on millions of images and learns to identify dogs from not dogs will be more helpful. So who are the audience?
So again, that depends on the interpretable representation. You can forego all of the technical details and just tell people if the ball is not there, the image would be predicted as this or that. So you don't really need to do all this. You don't need to get so technical about it, but then this means that you're losing out on a lot of context. So I would never ever show this sort of explanations to a lay audience because there are so many assumptions there and so many things that are done incorrectly that they are just misleading. They're wrong. Whereas they serve as a really good example to talk about explainability to more technical audience because I can show you all of these quirks and all of these bad decisions that you can make when designing or deploying them. So this is just used for demonstration purposes. I'm not saying that this is good or this is you should actually ever look at that again. I'm just saying there are so many problems. You should make sure that you know what you're doing when you're deploying or developing explainability. You had a question, right?
I think just a little while ago you said what my problem is with this. I mean, in general in the field, the attempt is to do this all completely data-driven, like you said, just take input and output, and you construct something. But you also did mention that a better explanation is if you have background knowledge, because, like you said, if you could recognize the eyes and the ears and those. But then you're saying, oh, but that's too hard. You have to handcraft them. But isn't the thing is that the way that we should be going is developing systems that can construct the background knowledge and do predicate invention and feature construction automatically. Because it seems like the argument is, well, that's too hard, so we'll just stick with doing input-output data-driven because it works, but it doesn't really, because it does something, but not really what we want.
Yes, so whatever you get out of these methods, these look like explanations, but these are not. They are probably even incorrect and misleading. But then for images, for example, you have to go, at least in this case, ideally, if you want to make them, these methods work, you have to go case by case, and possibly the segmentation even differs between two people. You may be interested in something completely different. So for example, if you want to check the robustness of your method, you would separate the object in the foreground from the background because, for example, you want to see whether the snow in the background affects the classification. So you would focus on a different thing. For tabular data, it may be a bit easier because, like you said, you can do something more creative about partitioning the features or putting together, bugging some of the categorical attributes that are similar. Or, for example, you could transform a numerical feature into a categorical feature and then deal with that. So, for example, if you're dealing with, I don't know, some medical information, you know what the threshold is for a healthy person, you could easily split that. Below that it's unhealthy, above that it's healthy, and you could communicate in terms of these two categories as opposed to telling people, yeah, I don't know, the result of this test is 28, whatever that means to you. So then you could possibly automate this sort of things. But again, it is on case-by-case basis and it requires effort. You can't just pull one of these off the shelf, deploy it, and there you go. It doesn't work. Yes, so we still have a long way to go.
So I have a question about the evaluation. So do you think the explanations should be faithful to the models we want to explain, or they should be similar to what people want the models to reason.
Well, I don't think you should reaffirm people in their biases and incorrect beliefs, right? So if you're trying to figure out what the model does, then they should be truthful with respect to that model, which does not necessarily mean that they will be correct in terms of the general world, right? Because if your model is incorrect in predicting something, then the explanation will be for the incorrect thing. So this may not correspond to your idea of what is happening, and that's not because you are wrong. That's because the model or the explainer can be wrong. So you need to take that into consideration as well. Does that answer the question, or?
For example, there are some research they evaluate the explainers based on does the explanation is correct to what to the labels people predefine, and some will evaluate the explanations based on the fidelity, right? So I think my question in general is like how should we evaluate the explanation?
I wish I knew, but the best I suppose you could do is, first of all, make sure that the explainer is correct. It's not stochastic. It is consistent. So make sure that the technical part of the explainer is all taken care of. And then only then move on to actually visualizing these things. Because from one numerical insight generated by an explainer, you could generate a bunch of different visualizations, right? And then some of them may be better suited for the application, the audience, the context, the background knowledge that people have with. For example, if you assume and you know that people will come with a certain background knowledge, then you don't really need to include that in your explanation because that's redundant information and you may be overloading the explainees. So any sort of validation, benchmarking, or anything does not really tell you much unless it's executed in the exact same context, the exact same scenario with the same audience as you're planning to deploy your system in. I don't think there's one solution or one validation technique that can account for all of these different properties and aspects.
I think there are 2 questions remaining from Ed. Oh, Ed, I wonder if you could unmute and ask, or otherwise I'll ask. I don't know if that works. Okay, that might not work. Right. So I'll pick one of those 2 questions. So it seems that the methods are actually explaining a pre-trained model. So what about work being done on unpacking the training process or training the explainer or the surrogate in parallel? So you could potentially then train the explainer to provide better explanation. So then also, or you can maybe have better understanding of the model's reasoning process. So is there any work on that line?
Not that I'm aware of. Like I said, ideally, you would want to train an interpretable model from the outset if you're trying to solve a problem, right? Because surrogates and any explanation that is not derived from the predictive model itself. So if you don't make it transparent, if you only base the explanation of the inputs and outputs, you can't guarantee that it is truthful, that it conveys the information that that is based on the same insights that the model is using to predict. Again, it depends on how you split the image, how you generate all these things. So again, just to make sure that it's clear, this look like explanations, but this may not necessarily be explanations. If you know all of the assumptions that they operate under, you can kind of judge their correctness. You can tweak the situation and you can tweak the setup of your model, of your explainer, such that they are the best that the model can provide, but they may not necessarily be truthful. And just to give you one very simple example, generating these explanations with a linear model based on superpixels is incorrect from the outset, because with linear models, you assume that your features are independent. Whereas here, your features are adjacent superpixels. So this already, there is some information leakage between the adjacent superpixels, and this is not taken into account. That's why with some of the explanations, you've seen that if the ball is being highlighted as an important region, a lot of times segments around it are highlighted as well, just because they're an integral part of the ball or part of the image. So you break already one of the most fundamental assumptions of linear models, and you're kind of hoping that whatever you generate are truthful explanations.
Given all these surrogate explainers are so brittle, do you think we should go on just, specific model-specific explanations? So if you're using transformers, then we should build an explainer that will fit within transformer model or convolution base or whatever that is, decision tree base.
That's an interesting one, because it touches upon the distinction between ante-hoc and post-hoc explainability, which I think is not very precise. Because when people say ante-hoc explainability, ante-hoc interpretability, they mean that the model that predicts is transparent, is interpretable. But this is not necessarily the case for ante-hoc explanations. So for example, if you're operating within a model-specific context, you know how the model works, you know what assumptions the model makes. It may not be transparent itself, but you may know how to extract certain parameters or certain insights, and then present them such or process them in a robust way such that it provides you with an explanation. This is not considered ante-hoc per se, right? Because you're doing some processing. The model is not transparent. But if you know what you're doing and if it's consistent with the assumptions, then I think this would still constitute a valid explanation. So I think, yes, we should either design interpretable models from the outset, or we should focus on methods that are dedicated for particular models, use cases, scenarios, assumptions, and we should make all of that clear.